Good morning. My name is Arnaldo Tavares. I'm a Senior Business Development Manager of Nvidia responsible for Latin America. Although Brazilian, I'll do the presentation in English as requested so we can reach a broader audience. If you have any questions at the end, I'll try to save at least 5 minutes for a couple of questions. And if you have any more questions, please look for me after the presentation. So the idea here is to talk a little bit about the path to Exascale, how we are at this point with Nvidia on the way to reach Exascale, and how new technologies introduced by our CEO during our event called GTC, GPU Technology Conference, in March this year, are going to help us reach there. And I end the presentation talking a little bit about how can we learn as investment in HPC in Brazil, how can we learn from the other BRIC countries, what they're doing, how they're evolving, and what we can do here in Brazil to expand our HPC investments. So I want to begin with this slide. This slide was shown by Jensen Huang, our CEO, as his keynote on Supercomputing 2011, when he talked about the path to Exascale. You can see here that if we compare the lines, the blue line using CPUs only, or the green lines use GPUs only, you see a big difference on the use of accelerators like GPUs. If we consider the evolution of CPUs, the way they were evolving during those years, we expected to reach the exaflop only in 2035. While if we're considering the use of GPUs, we believe we can reach the exascale with a limit of 20 megawatts by 2019. So we're going to talk about the technology Nvidia announced recently that will help us reach the exascale around that date. So one thing for sure right now is we're calling the era of accelerated computing. We cannot consider any further expansion of HPC without any type of use of accelerators, whatever they are, Nvidia GPUs, other types of GPUs, or even accelerators like Xeon 5 from Intel. We know for sure that accelerators is the way to go. We also can see that GPUs have a big use in terms of HPC, and this use is expanding in every new list of the top 500 that is announced. Next one is to be announced now in June. We see that from the last list, 19% of all flops on the top 500 list comes from GPUs. And you see that for whenever new version comes out, in this case the Kepler version on the bright green, you see the use and expansion of that in terms of flops is higher and higher. So we can expect the same with the next architectures that are coming. One of the important use of GPUs and the reasons why users use GPUs in top 500 is because of the energy efficiency. That's key because of how we can overcome the issue of the power wall. And we can see how GPUs are good with that. This is the list of the green 500, the most energy efficiency HPC systems. And we see that GPUs got all of the 10 top spots on the green 500 list, showing that it's really a good technology in terms of energy efficiency. And that evolution will continue in the next few years. This slide was presented recently on GDC, showing the evolution of Nvidia architectures for the GPUs. We are right now at Kepler architecture, as we all know, with the K20, 10, 20, 20X, and K40, more recently announced. And that will continue to evolve over the next few years. This year, we launched the Maxwell architecture, initially only for the GeForce, the gaming models, but the architecture will also come to other product lines like Quadro for professional visualization and Tesla for computing. The big advantage of Maxwell will be the higher performance per watt. As I mentioned before, energy efficiency is key, so we're always looking into improving that with the next architectures. But in this talk specifically, I want to focus on the next version of our architecture expected for 2016, called Pascal. Pascal is a big leap in terms of new technologies that Nvidia is introducing in the market. And I'm going to show you some of the announcements that our CEO made last March and how those technologies will help us reach the exascale by 2019. So one of the announcements we made during GPC is the use of GPUs on machine learning. Turns out GPUs are also, due to this high parallelization, a very good tool to expand and accelerate machine learning. Neural networks, artificial neural networks, can really be accelerated with the use of GPUs. And we presented an example of comparison with Google's project called Google Brain, where they used 1,000 CPU servers to teach the machine to think and learn like the human brain thinks and learns. So that project cost about $5 million and power consumption was around 600 kilowatts. And recently, the Stanford University, the AI lab, developed a system, a machine learning system, with similar performance to Google Brain, but using only 3 GPU accelerated servers with 4 GPUs each. So the power consumption, obviously the cost, is completely different, really proving that GPU is a great way to go to machine learning, which is one of the hottest topics right now in scientific computing. One of the announcements we also made is the partnership with IBM to expand the use of GPU computing beyond x86. Customers will this year now have the option with an alternative to x86 for use of GPU computing. So the Tesla GPUs will be available with Power 8 until the end of 2014. We'll have the first versions of Kepler accelerating power-based machines. Additionally to that, the 2 main technologies I want to talk about today are the ones that were announced also for Pascal in 2016. First of them is the stacked memory. One of the bottlenecks in accelerated computing in general, or more specifically in GPU computing, is memory bandwidth. We know memory bandwidth on GPUs is already very high. It's around 250 gigabytes per second. But that's not enough. With the growth and expansion of the number of cores, with the parallelization of the GPU, which now can reach 2,880 cores for every single GPU chip in a K40, for example, we need more and more memory bandwidth to be able to feed all these cores with the needed data. So stacked memory will allow us to expand this memory bandwidth much further. The idea, of course, is to stack the memory chips in the same encapsulation of the GPU. And that will provide much higher bandwidth. We expect to reach closer to 1 terabytes per second. Much larger capacity, obviously. And another important point, much more energy efficiency, as the bits doesn't have to travel further in and out of the chip encapsulation. So this will improve tremendously the performance of GPU applications inside the GPU, and also energy efficiency. Another big issue in the use of GPU computing, obviously, is the well-known PCI Express bottleneck. When we compare the memory bandwidth we have today with CPUs and GPUs, when we compare the 50 to 75 gigabytes of memory bandwidth with the CPU, and a much higher with the GPU, we see that PCI Express can really become a burden with certain type of applications that demand a lot of communication through the PCI Express. So that was an issue, an imbalance between bandwidth that needed to be solved. So that's why Nvidia introduced another technology we're calling NVLink. NVLink is a technology that allows much faster communication between GPUs and between the GPU and CPUs that will support this technology. NVLink will be composed by links of 80 gigabytes per second, So we can reach, when it evolves, all the way up to 200 gigabytes per second. And we will make it closer and try to fill this gap and eliminate this bottleneck of the PCI Express. So now, with the first implementation of NVLink expected in Pascal, we'll have a similar bandwidth between the CPU and GPU communication and the GPU memory bandwidth. As the memory bandwidth evolves in the CPU, obviously not only in x86 but in other technologies like power, NVLink will also evolve at the same pace, so we have a more stable and more comparable level of bandwidth. When we add that up with the expansion of memory bandwidth of the GPUs with the stacked memory, we can see how we're going to tremendously increase the GPU computing performance of new applications with the introduction of Pascal. So stacked memory and NVLink are the two main new technologies that are going to be introduced with the Pascal architecture that will allow us to get closer to reach the exascale. As I mentioned before, another benefit of NVLink is that we'll provide to the market another alternative to x86 with the use of GPU computing. So nowadays, you'll be able to connect the Kepler architecture to x86, ARM64, or Power 8 using PCI Express. But from around 2016, with the introduction of Pascal, we'll be able to connect to ARM64 and Power 8 with the use of this new and faster bandwidth. So that will make the alternatives to x86 even more interesting to the HPC market. Another benefit of the new Pascal architecture is the opportunity to create different form factors. Jensen Huang, our CEO, is seen here holding one of the Pascal SXM module, introduced this new module also on our event in GTC. This module is much smaller than the traditional GPU card that we all know. So as you can see on the diagram here, in the space that today we introduce a single GPU in a workstation or a server, we'll be able to introduce, actually use and connect 4 GPUs. So that will allow us to solve another problem, which is extending the number of GPUs per server. We'll be able now, in a one-use system like we have here, instead of using only 2 GPUs per system, can use 4 or maybe even 8. Expanding with this the possibility of a faster GPU performance intranode. One of the things we know is that as GPU applications evolve, they're demanding more and more performance intranode and between many nodes. So Pascal will also help us with that, increasing the number of GPUs per server. That was one important introduction in terms of Pascal. We also announced on the ARM world, new development will also help a lot future HPC implementations. In the past, we had what we call the GeForce architecture, which is the GPU architecture used by GeForce, Quadro, and Tesla, separated and independent from the mobile architecture, which is we call the Tegra products. But with the introduction of the new product, Tegra K1, we were actually able to connect all architectures, having from now on a single architecture that will be able to use from the mobile device all the way up to HPC. So that's Tegra K1. With Tegra K1, as you can see in the diagram here, we were able for the first time to take an entire SXM, as we call the stream multiprocessor, with 192 GPU cores and put that inside of a Tegra chip. What's the greatest advantage of that? The most important thing is everything we do today in a GPU, whatever is the GeForce type, a Quadro K6000 or a Tesla K40, we will now be able to do with the Tegra chip. So we can run OpenGL, for professional visualization applications. It can run DirectX for top gaming applications, but it can also run CUDA 6.0. And that's why this is such an important announcement for the HPC community. We now have the ability to provide GPU computing in a chip that consumes less than 2 watts of power in comparison with a GPU that nowadays consumes around 225, 250 watts. So that will also help increasing tremendously the energy efficiency for CUDA computing. We announced 2 versions. One version, the 32-bit version, is already available in the market right now. We recently announced a new Xiaomi tablet in China. That's the first tablet that will have the Tegra K1 available. And later on, probably by the end of this year, we will announce the new version based on the Denver project, which is an Nvidia project for implementation of a 64-bit version, 64-bit ARM version of the Tegra chip. As I mentioned, the 32-bit version is available right now. So for developers that want to port applications from x86 to ARM, or want to start using CUDA computing in Tegra, they now have a development board we call Jetson TK1. Jetson TK1, as I mentioned, is a development board, and it comes not only with the hardware for that supports CUDA 6.0 computing, but also with the library for specific applications of computer vision. So you have some algorithms for computer vision embedded in the system. So this has been tremendously used by the automotive market right now. During GTC, our CEO introduced this implementation of Jetson TK1 with Audi in a self-driven car that came in the stage to present the technology. It's a very small board. It has very low power. So for developers that want to begin to use CUDA on ARM, is a great way to start. And it's also available. Some people ask about price. It's very easy to remember. $1 per core, so $192 is the cost of this board. So very easy access for developers that want to use CUDA on ARM. So with this, we believe that we can provide the energy efficiency and the performance needed so HPC continues evolving to reach the exaflop system by 2019. This is the Tegra Roadmap. We are now here. The architecture called Logan is now officially called Tegra K1. We're going to have new versions even faster than that. Next version should be the Parker one, already with the Denver CPU, the 64-bit version I mentioned, and also with the Maxwell GPU. So the idea is to continue to have a single GPU architecture for the entire line. So we're going to, as ARM evolves, we're going to see more and more implementations of ARM, all the way from mobile devices to servers. So it definitely, at one point, will reach the HPC market. To finalize, I want to show a quick comparison I did back in 2012 in a regional HPC event here in Brazil, where I compared Brazil, that had 3 HPC systems in the top 500, with other BRIC countries, including South Africa. So as you can see, we were behind the other BRIC countries and way behind China. Let's see how this evolved during these 2 years. We're still with 3 systems. South Africa was out. Russia evolved a bit. India evolved a lot. And China, although reduced the number of systems, increased tremendously in terms of the top system. They are back with top 1 system. India and Russia have very high numbers as well, top 500. And Brazil is now only at 156 system with a GPU-based system called Grifo 04 at Petrobras, the local oil and gas company. But as you can see, we're still far behind the other BRICS, so there's a lot of room for improvement if we invest heavily in HPC. And we can learn a lot specifically from China. I also took another graph from the top 500 list website, where it shows the performance share per country. Obviously, US is much bigger, but I want to show specifically how China evolved all the way from 2001 or 2002, when they were basically zero in terms of performance share, all the way up to 20% in about 10 years. And most of this evolution in terms of performance per share came from the use of accelerators. I don't know if you remember K1, the first top one supercomputer using GPUs back in supercomputing 2010. It was the first implementation of accelerators by China, but they continued doing that. The existing #1 today also use accelerators. So China really showed the way to the rest of the BRICS, how you can evolve fast, how you can close the gap with European countries or the US if you invest heavily in accelerated computing. So that's one thing we can definitely learn on the other BRICS, and especially here in Brazil, to catch up with the other countries in terms of HPC implementations. Thank you for that.